All right, here we go, locking in. Do you guys notice as you walk through this space right here? It's weird.
Nope.
Like you all passed through it. Like your head is like you feel it. Okay, so check it out. Tennis ball has mass, has inertia. Tennis ball's at rest. What does the inertia want to do? Stay at rest.
It's called gravity.
Dude, check this out. I mean, it's been doing this all morning long. It's like right here. Crazy. It's as if something's like.
It's called gravity.
And breaking character. Vincent is right. It is gravity. Okay. Now, question. The tennis ball has force of gravity at this location. Yes, there's force of gravity at this location. If I take away the tennis ball and I take away all air molecules and there's just this space right here, is there still a force of gravity in this location?
Yeah. Yes. No.
I'm going to argue no, there's not. Because, for this reason, there are not two masses. Earth, we've got that. There's nothing else there in this location if we get rid of all air molecules. But I will say there is a gravitational field in this location, as there also is all around the Earth. Okay? And if we take something with mass and we stick it in the gravitational field, then there will be a force of gravity. You all right with that? Okay. So the gravitational field is kind of like the promise of a gravitational force. There's no force at this point, but there will be if you stick something with mass at that location. How are we doing there? Okay. I'm trying to use stuff that we're more familiar with to dive into stuff that we're less familiar with. You all right with that? Okay. Okay, may I introduce to you the Van de Graaff generator?
Look, Tesla coil. Well, no, it's a friction coil.
So here's how this works.
Oh,
There's a plastic spool down here and a rubber band conveyor belt. Electrons like the rubber band more than the plastic spool. So electrons are put on the rubber band, it's transported up here. There's a metal comb, acts kind of like a harvester or a combine that takes the electrons off of the conveyor belt rubber band. And then there's metal tabs that go along here that touch this aluminum sphere. Okay. Where do electrons go on a conductor? To the outside. Okay. So this is becoming charged how? Positive or negatively? Negatively charged. Okay. Good with that? Okay. When charged, there's something weird around that space. Okay. Neutral peanut. Talk me through this. Charged how? Negative. Okay. What's going on inside the peanut right now? There's attraction. What's going on to the electrons inside the peanut? They're on the far side of the peanut. Okay. It's still neutral, but it's attracting because of polarization. Now, when I take my finger and I touch it, what is now the charge of the peanut? Positive, negative, or neutral? It's now positively charged. I took the electrons. You okay with that? Okay. We're going to call this a test charge. You all right with that? Okay. This is going to be our scout. Okay. Scout. Yes, sir. I want you to scout out the area. On it, sir. Do-do-do. Looks good over here, sir. Do-do-do-do-do. Okay, over here. Do-do-do-do-do. Oh, sir, getting some readings. What do you mean? I don't know. It's just kind of weird. Okay, well, be careful. Okay. Do-do-do-do-do-do. Oh, sir, this is crazy. Like, what happened? I don't know. I don't know, sir. It's just weird. It's just something. Yeah. Okay, well, be careful. Careful. Do-do-do. Weird, sir. I'm getting weird readings, sir. Sir. Okay, careful. Scout. Scout. Lost him.
Really died. Some random kid's gonna see this on YouTube later.
Why does the voice remind me of this small villager
That was the original Roman Fun Element Animations channel on YouTube.
That's my inspiration.
No way. I actually got no inspiration.
All right, so here we go. Hey, Santa Claus.
Yeah.
Thank you. How you feeling?
Okay.
Yeah?
Yeah.
I mean, you're walking. That's great.
Yeah.
Thank you. All right. So by the end of this lesson, you'll be able to describe the difference between electric force and electric field, discern which equation to calculate the electric field, and determine which direction electric force and the field are pointing. Okay? So we just had this conversation about gravity and electric field. So the way I'm going to describe an electric field is the promise of an electric force at a location. Promise of an electric force at a location. Okay? It's kind of like so like around the Van Graff generator, the weirdness of space, there's a promise of an electric force. If you take something with charge and you stick it in the electric field, it will experience an electric force. In this case, what we just saw demonstrated was an electric force of attraction. There was no force prior to that until you stuck something with charge in the electric field. There's a promise of that force, though. And that promise was realized, fulfilled, when we stuck something with charge in that electric field. Okay? Another analogy is like a beware of dog sign. Okay? If you come up to a fence that has posted beware of dog, are you experiencing the dog? No. But you walk in that fence, guarantee, like, what are you going to experience? The dog. Okay, it's the promise of a dog. If you walk into that fence. Good? Electric field. Oh, your neighbor.
Oh, yeah. Next to it.
Okay, what do you say? Okay, correct answer is B. The reason why is for the same reason as we just discussed with gravity. In order for electric force, there needs to be two charges, Q1 and Q2. You just have one, you just have an electric field. Right with that? Okay, so B. So here, I put some numbers to the demonstration. Okay, the charge on the peanut, positive 3 microcoulombs. Charge on the Van de Graaff generator, negative 250 microcoulombs. They're 70 centimeters apart, 0.7 meters, and experiences a force of 13.76 newtons. One of the things that makes electric field challenging for learning this are there are two equations. Electric field is equal to electric force over a charge, charge of 1. And then there's also electric field is equal to constant times Q2 over D squared.
E is the same thing, basically.
D is the same thing as Coulomb's law, yep. Distance, okay? So, question. Intuitively, as you go away from the Van de Graaff generator, so the Van de Graaff generator is creating this weird space. As you go away from this Van de Graaff generator, what do you think happens to the strength of the electric field? Does it get stronger or weaker? It's weaker. Does that make sense just intuitively? Okay? Which of those two equations are describing that the electric field gets weaker as you move away from the charge? The blue or the red? The red one. Does everybody see that? Okay. So this is that's how I organize it in my brain. Q2 is the charge on object creating the electric field. The charge on the object creating the electric field. Okay. It's usually the larger charge. In this case, it's going to be your Van de Graaff generator. Okay. This is the thing responsible for making the space around there weird. Okay. It's the thing that, yeah. Versus Q1, this is the charge on object experiencing or in the electric field. So the charge of the object experiencing in the electric field. This would be, this is a smaller test charge. And in this case, it was the packaging peanut. It was our Scout. Okay. The Scout was in the electric field, experiencing the weirdness of space, of the electric field. Experienced the force because it was placed in the electric field. It was a second, like it was the other charge. Does that make, see the distinction between there? Okay. So, what I want you to do this half of the room, I want you to answer and calculate. You're gonna pull out, everyone needs to pull out their calculator. Calculate, like, answer this question. This half of the room, you guys are answering this question. That's when you gotta answer. For sake of time, this half, you use the blue or the red? Guys all use the blue? Okay. So electric field, you've got 13.76 newtons over 3 microcoulombs, so 3 times 10 to the negative 6th coulombs, because it's micro and you convert. And so you found that to be 4.86, is like 4 million, yes? Okay. 4.86 times 10 to the 6th power, so 4 million. Now, a big distinction between first semester and last semester, first semester and second semester. Last semester I was able to ask you, hey, does that make sense? And you're like, yeah, or no. This semester, you're like, I have no idea. Okay? To give you a kind of a feel for this, electric field values are going to be large. They're going to be in the thousands or millions, somewhere in there. Big numbers. Okay. Second thing, what's the unit on this? Newtons per coulomb. Okay, see where that came from? Here's a big suggestion. Very strong suggestion. For the units in this, the rest of the semester, we're gonna experience some different units that aren't like meters or seconds and stuff. I would have an ongoing chart for every unit that you are writing down the measurement, the variable, and the units. And just update that as we introduce more and more measurements. Okay? You can have one, like a chart for every unit. Like, you don't have to have a huge chart for the entire semester, just have like, okay? So like, for example, charge would be the measurement. The variable for charge would be Q. The unit for charge is coulombs. The abbreviation for coulombs is a capital C. You right with that? Okay. So that would be, have that just going on the side. And you can update that as things are introduced. this half of the room, hopefully you chose the red equation. Okay. So you have 8.99 times 10 to the ninth times 250. I'm dropping the negative sign on the charge. That's what I always do. All over 7.7 meters. And I found that to be 4.86 times 10 to the 6th, the same value, meters per coulomb. Okay? On this, I gave you more information. You could have solved it either way. Usually on a worksheet, problems are on a test. Heads up, next Tuesday, not tomorrow, but a week from tomorrow. You will have to, I will give you just enough information, but slightly more. You'll have to make a distinction between which one's Q1 and Q2, which equation to choose, something in that regards. You will not get the right answer if you pick the wrong one. Okay, so part of my goal today is to give you a distinct, know which one, the blue or the red equation to use. Good? Questions there? That goes away.
Huh? Never mind.
All right, this one I'm totally just checking off a state standard. Electric field is proportional to 1 over d squared. That's the inverse square law. It gets weak very fast as you go away from it. That's all I need to know about that. Okay. This is, you are drawing the answer from the pre-quiz video. Correct answer is A. Good with that. That's just, okay, so this is just a memorized thing. Okay? So positive creates outward directed fields, negatively charged objects create inward directed fields. Okay, here's a freebie for you, help you memorize that. Okay? Positive creates sunshine, outward directed fields. Okay, and negative is like inward. Okay, hopefully that sticks with you the rest of your year. You can draw from that. You're welcome. Okay. There is nothing moving in the direction of the electric field. We've just drawn them as arrows to make a distinction between positive and negative created fields. When your parents gave you a name, we didn't question it, we just went with it. We memorized it, and we were like, okay. Whoever made this convention. Negative creates inward directed fields, outward created outward directed fields, positive creates outward directed fields. And we're like, okay, we just went with it. Nothing's moving in that direction. Okay? It's just a way to make a distinction. Point X is right here.
Oh.
Got a stapler that works. So excited. Anybody want a stapler that sort of works? Free. It's a high quality stapler, other than the fact it doesn't staple. Correct answer is D. Everybody good with that? Sunshine, radially outward. Good? All right, give that one a shot. Have a conversation.
But it's negative. Oh, should I be scared? Oh, okay. No, okay. Right. Thank you for the warning.
Correct answer is. Everybody go with A. Okay. So, a negatively charged object is repelling from an unknown charge. The unknown charge has to be negative. And negatively charged objects create inward directed fields. That's the type of detective work that you're going to have to do on the worksheet. Reading the context clues, trying to figure out what charges are what's the electric, that type of. Okay? Good with that? Okay. Example problem. You have object A has a charge of positive 2 microcoulombs 10 centimeters away from object B, which also has a charge of positive 2 microcoulombs. What's the net electric field 4 centimeters away from object A, between object A and B? Okay? So before we just dive into numbers, let's strategize. Is object A creating an electric field or experiencing an electric field at point X? It is at point X, we're trying to find the strength of electric field that is created by object A. So are we going to use the blue or the red equation? We're going to use the red equation to find the strength of electric field at X created by A. Then, looking at object B, is object B creating or experiencing an electric field at point X? It is also creating an electric field at point X. Okay? If I were to ask, hey, how much force is object B have on it due to A, then that would be experiencing the electric field. But I'm asking for the strength of electric field at point X from point B created. There's no secondary charge at this location. It's just a placeholder in space. Okay, so I'm going to use the red equation twice. One for A, one for B. Okay? How are we doing on that? Okay, so I'm going to have the electric field from A, so 8.99 times 10 to the 9th times 2 microcoulombs times 10 to the negative 6 coulombs. Converting that, it's 4 centimeters away, so 0.04 meters. Converting that to meters, squaring that, and I get that to be 11 million. So 11 times 10 to the 6th newtons per coulomb. Trust me, I calculated that first out. Okay? Which way is the electric field from A pointing at point X?
Oh,
To the right or to the left? It's sunshine, so it's going outward, to the left. Sorry, to the right. And I'm just gonna put 11 there, just to. Okay? How we doing there? Object B is also creating its own electric field at point X. And we can calculate that in a similar fashion. Okay, 2 microcoulombs divided by distance of separation, 6 centimeters. Bless you.
thank you.
And we find that to be 5 million newtons per coulomb. Which way is the electric field pointing at point X by B, object B? To the right or to the left? Sunshine, so at X, it's going to the left. And that's going to have a magnitude of 5. Okay? So the net electric field is going to be what? Tell your neighbor. Combined electric field of the blue and the green.
Oh, yeah.
Net electric field is going to be 6 million. Because they're going in opposite directions, find the net, the resultant, okay, to the what?
Right.
Right. How are we doing there? Okay, they're pointing in opposite directions, so subtract them. Find the net field. And the winner is whoever is bigger. Okay? Questions there? I'm going to use this as kind of a stage to help explain some other stuff. Good? Now, this looks overwhelming. Don't get overwhelmed. It's not too bad. Object A is creating its own electric field throughout space, and that's the blue arrows. Okay? Object B is creating its own electric field that goes throughout space, and that's the green arrows. The resultant of the green and the blue, doing head to tail, is the red. The net electric field is really what we care about at the end of the day. And the way we summarize that is we kind of, instead of like connecting the dots, we're going to connect the lines. And we create what are known as electric field lines that summarize the net electric field at various locations. I believe I spoke to that in the video. Characteristics of electric field lines. Okay. So, identical charges, your halfway in the middle. Correct answer, for the sake of time, is E. They cancel each other out entirely because they're equal distance from the same type of charge, therefore they have opposing electric fields and cancel each other out. Super special case. You okay with that? Have a conversation. Okay, this one is creating an electric field going which way? At this location. Outwards. Sunshine. Yes? This one, this charge is creating an electric field going which way? At this location. Inward. Because negatively charged. The resultant of those two at the tail is to the right. That make sense? Okay. Notice that one's negative. That's the difference between that and this. Okay? Thumbs up, you got something? For the sake of time. This one's positive, sunshine, this one's going in, this is positively charged. This one also has a greater amount of charge because there's more lines, the electric field lines are closer together, more densely packed, caused by a greater charge. B. Good? Last question. Nope. No, that's the last question. Have a conversation. Tell them why.
It's like, I don't really know what to write for now. Yeah. So,
Correct answer is A. The lines are really closely packed together here. Strong electric field. One's super spread out. Two's kind of in the middle. Good with that? Got a worksheet that's due tomorrow. Good job.